Okay, in this presentation we're going to look at hypothesis testing for the difference in proportions, okay? So a sample of children who were hospitalized as a result of a car accident, okay? Uh, so 280 of the children were not wearing a seatbelt and 98 of those were seriously injured. 130 were wearing a seatbelt and 26 were seriously injured. So we have two groups here, the not wearing seatbelts and wearing seatbelts. And our population is essentially children who were hospitalized as a result of a car accident. Now, I realize hypothesis testing questions are very long, but if you can sort of make a quick statement like that at the start of your solution, that would be helpful. Test the hypothesis that the rate of serious injury is the same for children who wear seatbelt or not. Okay, clearly state your null and alternative hypotheses and your conclusion, and use a 5% significance level. Just as a quick remark, we're always going to use 5% significance levels in these videos. Now that sort of just might switch around, but for a lot of undergraduate statistics courses, 5% is the typical level. Okay, so I won't vary that much. Now, just a sort of quick rundown of the general structure there. You can have a just sort of quick read of it, but I'm not going to read through it. I'm just actually sort of going to remark that that's the sort of format we're going to take. In this particular instance, we're going to use critical values though. Okay? So that's it. So we'll go through these 4 steps there. I'm not going to talk through them. The first step actually was statement of hypotheses. Okay? So the null hypothesis proposes that there's no difference in injury rates if the child wears a seatbelt or not. And the alternative hypothesis is that there is a difference in injury rates depending where you, or actually a child, wears a seatbelt or not. Okay? So this is how we might state the null and alternative hypotheses, that they're equal or not equal to each other. Okay? Now, a quick statement here about what the hypothesis means is helpful. Okay, not something a bit more detailed than that and relevant to the question. So you can actually just include something about seatbelts or injury rates or something like that. Just a sort of quick sentence like that, just to sort of be a bit more specific to the question asked. But really, it should sort of express population proportions are equal to each other or not. Okay, and then you just add a bit more context with it regard to the rest of the question. Now, this is actually a statement that people would find very intuitive, that they're equal to each other or not equal to each other. But I'm going to sort of re-express this statement with an equivalent. And in this case, what I'm going to say is that express it in terms of the difference in proportions. The difference in proportions is 0 or not equal to 0. Now, this is essentially the same as the statement I have above. Okay. Now the thing about this is that pi 1 minus pi 2, that's the proportions for both of children wearing seatbelts, or children who get injured if given that they wear seatbelts or don't wear seatbelts. Okay, all children. That is a difference, and that's actually essentially the numeric value of interest. It's the expected value under the null hypothesis, or the expected difference in proportions under the null hypothesis. Okay, now the test statistics. So there's a bit of calculation here, and in terms of, so this is the second of our 4 steps, and this is where most of the calculation is done. Okay, so essentially what we have to do is get our point estimate, and the point estimate is made up of the sample proportions for both groups. So it's 98 out of 280, which is the no seatbelts, and so no seatbelts and yes to seatbelts. Okay, just to have a little bit more added emphasis on it. P1 hat is 98 over 280, which is 35%, and P hat 2 is 26 over 130, which is 20%. Okay, sorry, I'm actually going to use percentages as opposed to proportions, and the reason for that will become clear shortly, but it doesn't really matter too much. Okay, now the point estimate is the difference in the proportions. Okay, and it's essentially 0.35 minus 0.20. Okay, now you can sort of pick this direction here such that it's always a positive number. But it doesn't really matter so much because, it's a sort of, the sign doesn't really matter a whole lot as long as you're consistent there. And what I mean by the sign is what do you subtract from what, okay? So you can sort of be a little bit self-serving there to make just sort of to give yourself a positive value there. It just makes it slightly easier for you, okay? Now, standard errors. Okay, so these are typically given in the back of the exam paper, and just as a quick remark that each hypothesis test would have a different standard error. And sometimes there's a different standard error depending if you're doing a hypothesis test or a confidence interval. And that actually would be the case in this instance, okay? So this is actually specific to hypothesis tests, okay, this standard error. So you should see a formula similar to this or mathematically equivalent to this in your exam sheet somewhere. Sometimes if you might have to actually memorize them. Hopefully that's not the case. Now, but what this will depend on is this calculation here is p bar and 1 minus p bar, okay? Now p bar is the aggregate proportion. It's the overall proportion, okay? Or the overall proportion of the aggregate proportion. It's essentially just disregarding what groups are involved, how many kids were seriously injured altogether, whether or not they wore seatbelts. So essentially what we do there is just like we have 410 children and 124 were seriously injured. So altogether 30% of the children were seriously injured, 30.25%. And again, I'm going to use percentages there, okay? So essentially what we're going to use is that value in our formula there to calculate standard error. So 30.25. Just as a quick remark, if we are using confidence intervals, we would not use this aggregate proportion. We'd actually use both sample statistics, both the sample proportions, okay, in the calculation. Okay. Now, that's our calculation for the standard error, okay? 30 times 30.25 times 69.75 times 1 over 120 plus 1 over 130. I sort of done this second component here, this part as a single calculation on the calculator, and I get 0.01126. I'm going to add in a few extra decimal places just to give yourself a little bit more accuracy so that if you check your answers, you can compare very closely to mine. Now, a bit of rounding error will come into play. The reason I use percentages is it just makes this number easier to work with, because if you work on the basis of proportions, okay, and then multiply, you get a very small number there, 0.0, I don't know, but it's very small. You will get a number there with a lot of zeros just after the decimal point, okay? And I just think that's just so easy to make mistakes. So that's why I prefer percentages there as opposed to proportions. It's particularly at this stage. So we should get a value of that is the square root of 23.7579. And again, a bit of extra decimal places there just to help you find it. 0.756 is probably fine. And we should get an answer close to 4.8742. And again, rounding error will come into play. Okay, so if you're in the ballpark of 4.87, we're good. Okay. Now, so the general structure of a test statistic. So for a lot of undergraduate exams, not every one, but if you're dealing with sample means or sample proportions, this way of remembering things is very helpful. That's the point estimate minus the expected value under the null hypothesis divided by the standard error. Okay. Sometimes I call that the null value. It's not exactly a null value. It's just it's to sort of distinguish it from the point estimate. Under the null hypothesis, the expected parameter value is the expected difference of the null hypothesis, that is 0, and we observed a difference of 15%. So. And our standard error there is 4.8742. So our test statistic is 3.077. Okay. Now that is something I should sort of put in there. A Z normal random variable, the test statistic with a standard deviation of a mean of 0 and a standard deviation of 1 squared. Okay. So that's sort of generally understood. If you want to get the 100% mark, and if you have time, you could just actually state something like that. Test statistic is a z random variable. Okay. So essentially, what we do now is go to the critical value part of this process. Now, these are generally found in statistical tables that accompany you when you go and do your exam. Just make sure you actually have the right tables, because sometimes they give you engineering tables instead of statistical tables, because they don't know what they're doing. And why would they? So just check that you have a bit of practice with the statistical tables, the people who run the exams. So essentially what we need to pick is our significance level, and I've sort of said previously that I'm going to be consistent about a significance level of 5% in the worked examples. I'm going to sort of use that as a fixed point just to make life easier. So working with critical values and quantiles from the Z distribution and T distribution is important, but I'm not going to do it in this video because it just takes too long. Okay, the sample size is relevant. Okay, and also the number of tails in the test, and is it a one-tailed test or a two-tailed test. The reason for that is relevant when you look up tables. It might ask you, you might have to sort of make an adjustment on the value given in the tables, depending on if it's on one-tailed test or two-tailed test. Now, so I've sort of gone on a bit there. Just to sort of a few quick remarks. I'm not going to go into any more detail in this. We have a large aggregate sample, okay, and that will always be the case when you're dealing with proportions, really, because it doesn't really make any sense if you're doing it with small samples to look at test proportions. It's not statistically valid. It's a two-tailed procedure, okay. How did we know it's a two-tailed procedure? Let's go back up here. Because it is equals versus not equal to, okay? And not equal to gives you two alternatives to the null hypothesis. That's essentially how you determine the number of tails, okay? So I won't spend any more time on that, because hopefully you're very familiar with this number of 1.96, and if you're looking at some of my other videos, I'm almost following that part of the video as a template, okay? It's 1.96. So 1.96 is our critical value. Okay, so our decision, do we reject the null hypothesis? Yes, we reject the null hypothesis. No, we fail to reject the null hypothesis. And essentially we're making a statement about how much evidence we have. Do we have sufficient evidence against the null hypothesis? Yes or no? Now, just as a quick remark, actually, it's probably a little bit hard to read there, but essentially we're not really talking about this. We're not really talking about if a hypothesis is true or false. We're just talking about strength of evidence. We might have very strong evidence, and it still turns out to be false, or and so on. Okay, that's just the sort of the hypothesis tests don't prove anything. Okay, they just sort of talk about the strength of evidence, and you still have to sort of continue your research process on beyond the hypothesis test. So is the test statistic greater than the critical value, where the critical value is the CV is the critical value? Okay, then we reject the null hypothesis. If the test statistic is less than or equal to the critical value, we fail to reject the null hypothesis. Okay, not enough evidence. So just actually something I should sort of state here. I actually should really correct that and sort of say is the absolute value of the test statistic greater than the critical value. It's sort of better if you actually get not better, but it's a sort of you're really considering the absolute value of the test statistic there. Okay, so here the absolute value of the test statistic is 3.08. Did that right? I don't recall that being my number. Yeah, sorry, 3.007. I just adjusted it to 2 decimal places. Okay. And that's greater than 1.96, so we can reject the null hypothesis. There is a significant difference in proportions. Wearing a seatbelt does play a significant part in injury rates. So just a little sort of conclusion like that at the end of your hypothesis test exam question would be helpful, because it's really, I realize that these questions can be very long and you have to look up tables and stuff like that, but if you can, just put in a little conclusion sentence. It does specifically ask for it in the question. Also, what might happen is that you might be asked for a confidence interval regarding this question as well. Okay, now, but that I didn't do that in this video. Okay, so that's good, we'll leave that there.